Okay, good afternoon. I'm Vivek from IIT Bombay. This is part of my thesis work, PhD thesis work. But before I begin, I would like to thank the organizers for giving me the opportunity to attend this discussion meeting and also present my work. I would like to talk about simplicity of spectral edges of periodic operators and their applications in homogenization, particularly the Bloch wave method of homogenization. Before I begin, I will just do a very quick recap of the Bloch wave method, and then I will talk about the spectrum of periodic elliptic operators and the kind of things that we have done in that area, and then some tools that we have developed in the spectral theory of periodic elliptic operators, and then how we use them in the Bloch wave method of homogenization. So I would like to mention that the Bloch wave method, the Bloch waves have been around for a very long time, but the Bloch wave method as a framework for homogenization was formalized by Konka and Vaninathan in 1997. Since then, it has been extended to many other situations, such as for non-self adjoint operators and also for Stokes system and for also for some non-periodic situations as well. For example, there is a recent paper of the group of Professor Vaninathan on Hashin-Strickman structures, where they have done a Bloch wave homogenization of Hashin-Strickman structures. So that's just a little bit about the Bloch wave method. So I will just do a very quick recap. So of course, we will consider operators of this kind, which are in L2 of Rd. And the assumptions on the matrix A is that A is real symmetric, and its entries are in L infinity sharp, by which I mean periodic L infinity functions. And of course, we assume the ellipticity condition, and and there's another set that I define, which is Y prime. So this set Y is called as the periodic cell, and this Y prime is called as the dual cell. Okay. So what Professor Muthukumar did last week, that I'm going to just run through very quickly. So first of all, he defined the Bloch transform, and using the Bloch transform, he decomposed the space L2 of Rd into a kind of field of Hilbert spaces indexed by eta in the dual period cell. So for each eta, you get a Hilbert space, which is L2 sharp Y. And we can write that decomposition in this manner. This is an isometry. And there is another notation for it. For those who know, this is also, this decomposition is also called as a direct integral decomposition, but I will not go into that. This Bloch transform also decomposes the operator A into a field of operators. So we get this operator called as a shifted operator, which is parametrized by eta and Y prime. And these operators act on this space. So this is kind of like this decomposition sort of distributes over the previous decomposition of the Hilbert spaces. So that's what we did first. We did this decomposition of spaces. And then what we did was we looked for the spectrum of the shifted operator A eta, and we obtain eigenvalues parametrized by eta, lambda m eta and phi m eta, which are called as Bloch eigenvalues and Bloch eigenvectors. And this can be written as a further decomposition of L2 of Rd. So basically this L2 of sharp Y, we're writing as little L2 of n. So this all we do at the scale at scale epsilon is equal to 1, but then we can go through the whole process once more for at the epsilon scale, and then the kind of decomposition that we obtain is this one. L2 of Rd is isomorphic to is the same as this is isomorphic to this space, which is this space. So we get Bloch eigenvalues and Bloch eigenvectors at the epsilon scale. And using the Bloch eigenvalues and the Bloch eigenfunctions, we can define the Bloch transform once more. And using the Bloch transform, our original equation, A epsilon U epsilon is equal to F, it transforms into this sequence of equations in the notation of Professor Muthukumar. And now if we want to obtain the homogenization result, we need to expand the first Bloch eigenvalue as a power series at xi is equal to 0, and then we pass to the limit. So that's just a recap. So what about the spectrum of the periodic elliptic operators that I want to talk about? So the first thing that I want to say is that the Bloch eigenvalues that are computed in the previous step, they are important for describing the spectrum of the operator A in L2 of Rd. So the spectrum of A can be in fact written in this manner. It can be written as the union of these intervals given by whose endpoints are the minimum of the mth Bloch eigenvalue and the maximum of the mth Bloch eigenvalue. And it can also be written like this. So this is a description of the spectrum of the operator A in terms of Bloch eigenvalues and Bloch eigenvectors. Further, we can look at the sort of maximal intervals here, and we can write the spectrum of A finally as a union of intervals. And for a proof of this, one can refer to Reed and Simon, volume 4, or one can also look in Dautrey-Lyon's volume 3, for example. So this is a schematic picture of this is a schematic picture, so this is not what actually it would look like, but this shows what the Bloch spectrum of a periodic operator would look like. So you can see that I have projected the range of Bloch eigenvalues on this side. So you can see that actually the spectrum of the periodic operator A will look like union of these intervals. And so what I'd like to mention is that these gaps in the spectrum of the periodic operator A, those are known as spectral gaps. And the endpoints of these spectral gaps, those endpoints are known as spectral edges. And the spectral edges are very important. In fact, it is the property of spectral edges which determines the homogenization. So here I'm just defining spectral gaps and spectral edges. And I'd like to say again that homogenization is in fact governed by the properties of the spectral edge. As you would have noticed, that in Bloch wave method, the homogenized tensor is given in terms of the Hessian of the first Bloch eigenvalue at xi is equal to 0. And therefore, properties of, so we require a lot of properties from the first Bloch eigenvalue. We require it to be at least twice differentiable. We require the Hessian of the first Bloch eigenvalue at 0 to be a strongly convex. I mean, it should be positive definite. And we require these kind of properties from the first Bloch eigenvalue. So yeah, like I said, for the first Bloch eigenvalue, we need at least that it should be twice differentiable and probably more. We also need some more properties. For example, we need the Hessian of the first Bloch eigenvalue at 0 to be a positive definite matrix. So this area where one considers parametrized eigenvalues which depend on a parameter, such problems, and then one considers their differentiability properties, such problems come under the heading of perturbation theory of operators, and it was developed by Relic and Cato. So I want to say that there are two main difficulties when someone is trying to prove the differentiability properties of parameterized eigenvalues with respect to the parameter. So as you can see, for example, all the information is available in the case of matrices. So if you consider this parametrized matrix for X in R, then this parametrized matrix has, we can write the eigenvalues of this parametrized matrix in two ways. We can write it as ordered eigenvalues, in which case it will be plus and minus modulus of X, or it can be written as plus and minus X also. But the problem is that in the case when we write it as ordered eigenvalues, the description of the eigenvalues in terms of the parameter X is not analytic, it's not differentiable even. Whereas if we rearrange the eigenvalues in this manner, then it becomes analytic. And then there is a second example, which is a two-dimensional example, an example which contains two parameters. And then we get these eigenvalues. These are the ordered eigenvalues. And the ordered eigenvalues are not analytic at this point. And there is no analytic rearrangement of the eigenvalues either. So what I'd like to mention is that the problem, where the problem happened was at the point where the eigenvalue changed multiplicity. So as we saw in the previous example, here the multiplicity of the eigenvalue was 2, and that is where the analyticity of the eigenvalues failed, ordered eigenvalues failed. And similarly, in this case also, here the multiplicity of the eigenvalue changes, and this is where the analyticity fails. But there is another interesting feature of this, which is that in this case, we are able to produce a rearrangement of the eigenvalues, which is analytic in the parameter. So what I would like to mention is that this is a general scenario. This always happens if you have one parameter. So if you have a problem which has one parameter, you can always rearrange the eigenvalues locally such that you can get an analytic description of the eigenvalues and even of the eigenfunctions. Whereas you have this situation where there is no hope, where there is more than one parameter. But of course, in most problems that we consider in applications, we always have multiple parameters. For example, in the case of Bloch eigenvalues, we have multiple parameters. So what should one do? So I'd like to mention the theorem that Professor Muthukumar stated, that the first Bloch eigenvalue at 0 is analytic in a neighborhood of 0. And we can also choose the Bloch eigenfunctions near 0 in an analytic manner. That happens only because near 0, the first Bloch eigenvalue is simple. If it was not simple, we would not have that analyticity. And in fact, there are cases of systems. For example, if you would want to do Bloch wave homogenization for elasticity system, or if you would want to do Bloch wave homogenization for Stokes system, you would not have that analyticity near 0. So this is a major problem in Bloch wave homogenization. So simplicity of Bloch eigenvalues near spectral edges, it is an important thing to have. But thankfully, there are some kind of results which say that if you do some kind of perturbation in the domain, or if you do perturbation in the coefficients, or you do perturbation in the boundary data and so on, then you can make the eigenvalues simple. So this is what we have done. We have done perturbation in the coefficients, which would make the spectral edges simple. So I would come to the statement of the main theorem that we have proved in a minute, but first I'd like to mention that not only is it the simplicity of Bloch eigenvalues near a spectral edge which is important, but there are two more properties which are considered in applications to be important. So for example, not only do we want the spectral edge to be simple, by which I mean that the spectral edge should be attained by only one Bloch eigenvalue, which is what happens for a single equation, for example, minus divergence A grad. But this does not happen, for example, for a system such as the linear elasticity system. Then the second property is that the spectral edge should be isolated, which means that it should be attained only finitely many times in the dual parameter. not infinitely many times. So this property, in fact, fails if you were to consider periodic operators on infinite graphs. But anyway, this is also an open question, whether this happens or not. And then there is another property, which is the degeneracy or non-degeneracy of the spectral edge. So which means that the spectral edge, the Bloch eigenvalues which are near the spectral edge, they should be strongly convex. So what is known, these are the three results. So Klopp and Ralston proved that if you have a Schrodinger operator like this, you do a perturbation in this periodic potential of the same period, then you will get a simple spectral edge. So you start with a spectral edge which is not simple, you do a perturbation in the periodic potential, and you will get a new spectral edge close to the old one, which is now simple. Another result about the finiteness of the number of points at which spectral edge is attained is by Filonov and Kachkovsky, who proved that spectral edge is attained at finitely many points in the dual parameter in dimension 2. So in higher dimensions, this problem is open. Also, there is a result of Parnowski and Sterenberg, who also proved in dimension 2 that if you have a Schrodinger operator of this kind, minus Laplacian plus V, and you do perturbation in the potential, but you do a perturbation with a larger period, then you can make the spectral edge non-degenerate, which means that you can make it strongly convex in the neighborhood of the spectral edge. So this is our result, where we have proved that if you start with an operator of this kind, minus divergence A grad, this is a single equation, not a system, and A satisfies the usual assumptions that it is a positive, definite, real, symmetric matrix. And then what we show is that if you do a perturbation in the coefficients, then you can get simplicity of the spectral edge. If it started out with something which was not, simple. But anyway, what I'd like to mention is the difference from the paper of Klopp and Ralston. Klopp and Ralston were able to prove this result for all V in L infinity. So if you take any potentials which are L infinity, you can get a new spectral edge which is simple. However, we have two results. One is that we would need to assume that extra regularity on the coefficients. Then the proof of Klopp and Ralston goes through. But that was not sufficient for our purposes because we wanted to apply this result in Bloch wave method of homogenization. And therefore, we wanted to do this for L infinity coefficients. So we started with coefficients of the periodic operator which were L infinity. But then we need to make an extra assumption, which is that the spectral edge is isolated. That is, it is attained at finitely many points in the dual parameter. And then we are able to prove that if you do a perturbation in a small perturbation in the coefficients, you can get a simple spectral edge. So this is a theorem that we proved. And then we wanted to use it for something in Bloch wave method of homogenization. No, so this perturbation actually came from Hahn-Banach theorem, so no. But we are looking at those kind of things also. For example, for a two-phase media, we would like to see if it's possible to perturb the domain, the interface between the two phases, so that it can be made simple. But yes, this is not computable since it's coming from Hahn-Banach theorem. So one application I'd like to mention if I have a minute. So what we saw was that in the Bloch wave method of homogenization, the Hessian of the lowest Bloch eigenvalue, it determines the homogenized tensor, and therefore the properties of the lowest Bloch eigenvalues were important for homogenization. And looking at this idea, Biermann and Suslina in St. Petersburg, they extended the notion of homogenization to internal edges of the spectrum. So as you can see, this is the lowest edge of the spectrum. And luckily, all the things that we want from the spectral edge, we want it to be simple, we want it to be isolated, and we want it to be non-degenerate. All of them actually happen to be true for the lowest edge. But they may, nobody knows anything about the internal edges. So they extended the notion of homogenization to internal edges of the spectrum. So what they do is they propose an effective operator at the internal edges, and they prove error estimates using the Bloch wave decomposition. So in their paper, they have assumed that the internal spectral edge should be simple, it should be isolated, and it should be non-degenerate. And then basically the effective operator, it picks up contributions from all the points where the spectral edge is attained. So in our paper, we have extended this notion for a spectral edge which has multiplicity greater than 1. I have not stated this result in this presentation since it's very complicated, but you can read it on arXiv, or it's also going to appear this year in asymptotic analysis. So yeah, thank you.